Okay, I now want to talk about what happens when we look at the difference between average and instantaneous rate as a limit, okay? So what we have here, we're looking at a function. The function is y equals negative x squared plus 16. It is an upside down parabola with a y-intercept of 16. And I've selected 2 points, a equals negative 3 and b equals 4. Those are both x coordinates, all right? And I've selected those x coordinates to show you how the slope behaves. For example, there is a moving further away from b, there's a moving closer to b, closer, 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 and finally they're right on top of each other. But notice the black line. The black line indicates the slope between these 2 points. Slope between 2 points, as I mentioned before, is called a secant line. Secant is Latin for sever. It cuts its way across the line. Now, another way to look at what we have here is we have a distance. And this distance is a change in x. It is a change in x. And each of these x points, though, also corresponds to a y point. There's a y point. I'll call that y sub 2. Here's a y point. I'll call that y sub 1. And the slope of that secant line, as I mentioned in the last video and in class, is y2 minus y sub 1 divided by delta x. Delta x is just another fancy way to write x2 minus x1. It's a change in x, so we're looking at a simple slope formula. And this all stays true even as point A here gets closer and closer to point B. Again, A and B are x values. So this relationship stays true. Now, there are a couple of ways to look at this. I'm going to clear this out and pick another point. That's a secant line. This is my secant line. It has a slope. This is another formula for slope. Slightly different way to write it. Okay, let me clear this information. Try to clear this information. There we go. Okay, let's move the points around a little bit. Let's move that one down now. This might be a little bit more clear visually. Maybe not. Doesn't really matter what 2 points we're talking about. Okay, so we're looking at this point, negative 4, 0, and this point, which looks like it is 2, 12. Okay, those both work out. So, yet another way to think of this is, here's my negative 4, 0, here's my 2, 12, and if I were looking at the slope between these 2 points, well, let's see. Here is my delta x. That means I started at an x value, and then I covered a distance of delta x, so I wound up at a distance I'm going to call x plus delta x. I started with an x value, I went a distance, I wound up at a new point, which I will call my original x plus however much I changed. Okay? If this is my x, the corresponding y is f of x. If this point down here is x plus delta x, then my new y value must be f of x plus delta x. So another way to write the slope of this secant line is it is f of x plus delta x minus f of x divided by delta x. In other words, my numerator is still some y value minus some other y value, and my denominator is still an x value minus another x value. It's just I'm writing my y values in terms of a y value based on the first x and another y value based on what happens when you take that first x and add some change of x. X plus whatever this change is gives me x plus delta x, which corresponds to a y, which we're going to call f of x plus delta x. Whatever you get when you start with x and add some change, what y corresponds to it. Happens to be 12 here, but the value isn't what's important. Now, what is important is what happens when we move these points around. Well, to that relationship, this relationship up here doesn't change. So let me show you what I mean by that. I'm going to erase some of this. Now let's see. Let's move these sliders around. Let's move my A value up to here. Let's move my B value down to there. And incidentally, up here, I have f of b minus f of a, again, y minus y, divided by b minus a, x minus x. Means the exact same thing as this way of writing slope over here. You have to be used to all the different ways we can express slope. Now as a starts moving closer to b, you see I've got this to tell me the slope. This g of a here, this tells me the slope of the instantaneous rate of change that we talked about last time. Now, as we get closer, right now the actual slope between x equals a and x equals b is -4. Instantaneous rate of change is 0. You can think of this as being like a softball at the height of its toss, where it's not moving up or not, nor is it moving down for a split second. Now watch what happens as they get closer. As a gets closer to b, so I can get the slider to move. As a gets closer to b, we get a slope of -5, instantaneous rate of -2, a slope of -6, an instantaneous rate of change of -4, a slope of -7, an instantaneous rate of -6. They're getting closer and closer together. The instantaneous and the average seem to be merging. But when we finally put A in the exact same spot as B, the slope is undefined. And this is a bit of a mistake on the part of programmers of Desmos, which is an amazing program. But this is really equal to 0/0 at this point. Because what's happening is, by making A and B the same x value, we're also making f of b and f of a the same y value. This is just y2 minus y2 over x2 minus x2, and 0/0 is in indeterminate form. And it can never actually be the answer. So I pick on Desmos for saying undefined when it's really indeterminate, but I have to give them credit for coming up with an algorithm that tells us what the instantaneous rate is. It's not supposed to be undefined or indeterminate form, it's supposed to be -8. That was what it looked like it was getting close to. Let me take a look at this. As we started back here at -3, we had a slope of -1, instantaneous rate of 6. Slope of -2, instantaneous rate of 4. Slope of -3, instantaneous rate of 2. Slope of -4, instantaneous rate of 0. -5 for slope, -2 for instantaneous. -6 for the slope, -4 for the instantaneous rate of change. -7 for the slope, and -6 for the instantaneous rate of change. We're getting closer and closer, and at the point where they should merge, the normal formula fails us, and there's something else Desmos is doing, which gives us the correct answer. Okay, how do I know this is the correct answer? I can figure that out several different ways. I'm going to share one of them with you right now. I'm not sure if this is what Desmos does, but the thing that was happening as I moved these, one way to look at it were the x values were getting closer and closer and closer together until they were right on top of each other. Class yesterday, Natalie described it as the 2 points destroying each other, like they were matter and antimatter. It's not mathematically accurate, but it's pretty funny. There's another way to look at what's going on. Another way to look at it is that the instantaneous rate is equal to a limit. It's the limit as delta x approaches 0. This is a little bit different from what we've done before. We've always talked about the limit as x approach something. Limits don't just have to be about a value of x. They can be about the distance between two x points. And what we're really asking ourselves with an instantaneous rate is as delta x shrinks, as our x values get closer and closer together, what happens to the corresponding y values and what happens to our distance? Now this apparently goes to 0 over 0. Remember I said a limit is like a dog on a leash. It's all about when you let the dog off the leash. If I allow the dog off the leash here, if I let delta x go ahead and reach 0, then this delta x disappears and I get f of x minus f of x divided by 0. Gives me 0 over 0, but that can never be the answer. If you get that for the answer, there's a trick you've missed or haven't learned yet. Let's figure out what that trick is in this particular case. Another way to look at what we're doing is we're finding the slope of a tangent line. I may speak more about that in a few minutes. Okay, this particular formula in this case, let's see what this looks like. F of x equals negative x squared plus 16. There's my f of x. I'm going to need that in this limit in a moment. Okay? I'm also going to need f of x plus delta x. Well, f of x plus delta x, this is something you don't want to overthink. If you know what f of x is and you're asked for f of anything else, for example, if this asked for f of 5, you would put 5 in for x. If this asked for x of q, you would put q in for x. But it's asking for f of x plus delta x. So I'm going to carefully put x plus delta x in everywhere I see an x. Okay. Let's see how this affects this limit now. Well, this limit becomes the limit as delta x approaches 0 of f of x plus delta x is negative x plus delta x squared plus 16, I'll put that whole thing in parentheses, minus f of x, y2 minus y1. My other y is negative x squared plus 16, all over delta x. A reasonable question at this point would be, how does this help us? And the answer right now is, it doesn't. If we let this dog off the leash here, delta x goes to 0. This goes away. My top two expressions are identical. This minus this will become 0. Delta x will go to 0. We would still get 0 over 0, but that's not possible, so there's still a trick I've missed. Now going to erase my general limit and get back to the specifics. Okay, well, luckily we've been practicing expanding things lately, so I'm hoping that fairly quickly you can see that another way to write this limit is the limit as delta x approaches 0 of negative x squared plus 2 times delta x times x. Let's see, yeah, plus delta x squared minus negative x squared plus 16 all over delta x. What did I do in here? I just expanded this binomial. I did it off the top of my head. You could use Pascal's triangle, you could FOIL. If you were feeling crazy, you could even pull out the binomial formula. You now have many, many options for this. Still not liking, oh, I left something out. I knew I was missing something. I left out inside, well, not quite. I left out plus 16 inside this parentheses, and my minus negative x squared plus 16 here. Fix my fraction bar. Okay? Still doesn't help much, apparently. Delta x goes to 0. This will go away. This will go away. This entire expression in these parentheses will still match that one, and subtraction will cause them to create a 0 on the top. We'll still get a 0 on the bottom. Nothing helpful seems to have happened yet. So let's keep manipulating the algebra. This is now going to equal the limit as delta x approaches 0 of, leave that in parentheses, negative x squared minus 2 delta x times x plus, nope, that'll still be minus, won't it? Have to be careful there. I'm distributing this negative sign, so that's minus delta x squared in parentheses. So this is still plus 16. Okay, close that parentheses. I'm going to go and distribute this minus sign to my second expression. So that's going to become plus x squared minus 16 all over delta x. Now, I'm still, if I let the dog off the leash, I'm still going to get 0 over 0. But some interesting things are starting to happen here. One of them is this. If I drop these outside parentheses, I will have a negative x squared and a positive x squared and a plus 16 and a minus 16. And now I'm looking at something a little bit different. I am looking at, let me rewrite it, equals the limit as delta x approaches 0 of negative 2 delta x times x minus delta x squared all over delta x. Now how is that helpful? It's not yet. If I let the dog off the leash here, delta x times negative 2 times x will be 0, because delta x will then be equal to 0, minus 0 over 0. Still not helpful, but very, very close to being helpful. Because I haven't let that dog off the leash, I must write this limit notation to tell anyone looking at it what I have and haven't done. What I'm noticing now, though, I have a common factor at every term on the top. I have a delta x here and a delta x here. I'm going to factor out that delta x. Now I'm left with negative 2x minus delta x over delta x. Well, there's still a problem. There's a hint in this problem. If I allow this dog to go off the leash now, this delta x will be 0, times anything will be 0. This delta x will be 0. I'll still have 0 over 0. But as long as I haven't let that dog off the leash yet, then delta x is not equal to 0 yet. Which means it still has a value, a common value to a factor top and bottom. It can be crossed out. And I will then be left with an expression that says equals limit as delta x approaches 0 of negative 2x minus delta x. Now see what happens. We've crossed out the common delta x to the top and the bottom. I can go ahead and let the dog off the leash now. If I allow delta x to reach 0, this is 0, who cares? I still have a negative 2x. Notice I did not write the limit notation again because I've allowed delta x to go ahead and reach 0. Negative 2x is what I'm left with. Now let's go back and talk about what the original question is. We have an answer. After this much algebra, a lot of kids don't remember what the question was. The question was, what's the instantaneous rate of change when we get to the point x equals 4? We have a and b both at 4, okay? And that's where the 2 points are on top of each other when we're at an x value of 4. So what would happen if we plug that x value of 4 in for negative 2? I'm sorry, in for x. We wouldn't plug it in for negative 2, that'd be weird. Negative 2 times 4 is negative 8. According to Desmos, the instantaneous rate of change when x equals 4 on the parabola, negative x squared plus 16, is -8. According to this crazy limit we just did, the limit of a y value minus a y value divided by delta x, it's just a slope. Did some algebraic manipulation. We got an expression with an x in it. We put the x value at the point where we wanted to know the instantaneous rate in there, and we got a value that matched Desmos. All right, let's see if we can continue doing that for a moment. A moment longer. Let's try some other values and see what we've gotten. Actually, at this point, I'm just going to erase everything. And now, let's see. According to Desmos, let's look at some different points. We've got our slope back now. I don't know. Let's just go back up 1 to 3. Okay. Yeah, b equals 3. According to Desmos, let's give me a second here. Oh, which way is it going? There we go. Okay. Now then, according to Desmos, if we take a look at this point, this is the point where x equals -1. I don't even care what y is at this point. What I'm interested in is the instantaneous rate at that point. The average rate between 2 points, as we discussed on Friday, is the slope of the secant line. As I may have briefly mentioned, the rate at a specific point is called a tangent line. So what I'm looking for is the slope of this tangent line. This blue line here is a tangent line, and its slope will represent the instantaneous rate, not between 2 points, not an average rate between 2 points along this function, but an instantaneous rate of change just at this point. Desmos says it's +2. Well, in general, let's see what we can do here. We can bring this point back. The average rate between A and B right now is -2. Move a little closer, it's -1. Move a little closer, it's 0. Makes sense. There's a horizontal line between those 2 points. The slope between them should be 0. Get a little closer, it's 1. Boom. Our slope formula goes to undefined, but it really means indeterminate. So this cannot tell us if this is accurate. What can tell us if this is accurate? Well, we just did a whole bunch of algebra. Good news is we don't have to do it again. We now know that the limit as delta x approaches 0 between -x plus delta x squared plus 16 minus -x squared plus 16 over delta x is always equal to -2x. We don't have to redo that algebra. If we want to know the instantaneous rate of change at the point x equals -1, we just know x equals -1, then this expression up here equals -2 times -1. The instantaneous rate at that point is +2. That is your instantaneous rate of change. Instantaneous rate of change, I said, was called the derivative. It has a notation. That notation is f prime of x. That's not a 1. Doesn't mean exponents. Has nothing to do with exponents. It's an apostrophe. It's pronounced f prime. And its formal definition is it is the limit as delta x approaches 0 of f of x plus delta x minus f of x divided by delta x. This is called the limit definition of the derivative. It's very important. It's what a derivative really is. We'll learn some shortcuts on Tuesday, but this is always what's really going on when you're talking about a derivative. If you're speaking about an instantaneous rate of change or a derivative, this is what is happening, and you will never be able to completely forget this definition for as long as you continue with math. I'm going to give you some homework that involves using this formula the exact same way we just did on some simple polynomials to find...
My search turned something up for as very poor as really is on Wednesday, Tuesday, but change order 4. Have a look.
I hate it when Siri interrupts. She's rude that way. I'm going to ask you to use this formula, following the same steps as the example I just did, with polynomials to make delta x disappear and find a general derivative, a general f prime of x, like this negative 2x for some simple polynomials. That will be your Monday night homework due Tuesday, and we'll go over some more of those examples on Tuesday. Hope this helps, and see you then.